important topic, grain refinement in aluminium alloys. What is the meaning of grain refinement? What is grain formation? What is grain refinement? What is grain size? All these things, metallurgical terms, you must be very well aware. Already you have studied your third semester subject that is called as material science. In that, again, you had already studied about the non-ferrous metals and their structures. However, in this subject, the grain refinement, how it can be done, and then in case of aluminium alloys, that we are going to discuss. Okay, grain refinement means, so this controls the grain refinement controls the mechanical properties of materials. In case of ferrous or non-ferrous, whatever it may be, grain refinement mainly controls the characteristics of that material. Whether the material is hard, material is brittle, material is ductile, or it has got high tensile strength or high compressive strength. All these factors are depending upon the grain size or grain orientation, grain refinement. So therefore, in order to have better properties, we should have the fine grains, and then how it can be formed, that is explained in this. Okay. Are you able to follow? Are you able to follow?
Yes, sir. Yes, sir.
So therefore, how does this grain refinement can be done? That we will see. Grain size is grain size in an aluminium alloy refers to size of individual aluminium crystals. Okay, what is the grain size? Size of individual grains or individual crystals in the solidified part. Once it becomes solid, in the solid part, what is the size of the grain? That will tell you about the grain refinement. The size of these crystals is directly related to the number of grains or nuclei formed during the initial stage of solidification. It means that the solidification process, while explaining that, I had explained that if the more number of nuclei are formed, nuclei you can see here, during solidification, more number of nuclei are formed in the liquid metal, the grain size will be smaller. If less number of nuclei are formed, then what happens? Grain size will be bigger. So you want smaller size grains, you want bigger size grains, coarse grain. It is called as coarse, C-O-A-R-S-E, coarse grain. Coarse grain, nothing but bigger grains. Fine grain means smaller grains. You want coarse grain or you want fine grain, it is all depending upon the number of nuclei which are going to form in the liquid metal. Larger the number of nuclei formed, then the grain size will be finer, and smaller the number of nuclei or lesser the number of nuclei, the grain size will be bigger or coarse. Coarse grain is going to be produced. So coarse grain is associated with some properties and fine grain is associated with the opposite characters of coarse grain. Like that, what type of property we want, that type of structure we should get. Okay, it means that what we can say is what we know. Without knowing inside, we cannot express outside. That is what internal structure is very important to show or to exhibit external properties. So therefore, this already it has explained finer grains, etc. as well. Thereon having the ability to promote improved casting soundness by minimizing shrinkage, hot cracking, and hydrogen porosity. So this can also control over this. So therefore, this grain size control, it is our refinement, grain size refinement. There are three methods are available. What are the to control the grain size? Whether you want the bigger size grain, that is coarse grain or fine grain, what type of grain you want. So that can be controlled by using any of this method or combination of these methods. Okay, so mainly three methods are available here. You can see one is thermal method. Second one is chemical method. Third one is mechanical method. So thermal, chemical, and mechanical. three tips or three methods are available to control the grain size. You want fine grain or you want coarse grain. So first, one by one, we will discuss what is the meaning of thermal method. So obviously, what comes to your mind when I say thermal? When I say thermal, what comes to your mind? Helrappa?
Heat.
Heat.
Heat, sir.
Yes, exactly. So when we talk about the thermal, so obviously we look at the heat. So we feel that something by controlling the heating factor or cooling factor, totally it is related to heat. So by thermal factor, how it can be, the grain size can be easily controlled. That is thermal method. So in this thermal method, it involves rapid cooling. It involves rapid cooling. Rapid cooling means what? Rate cooling at a faster rate, not the normal rate. Cooling at faster rate is called as rapid cooling. So therefore, thermal method, it involves rapid cooling. It is also called as chilling. Okay, chill nothing but very, very fast cooling of liquid metal and subsequently variation of process variables, controlling the process variables. Okay, then fine equiaxed grain structure arises when casting is carried out in cold molds under low superheating conditions. These are very important. Fine grains are fine equiaxed grains. What is the meaning of equiaxed grains? Equiaxed. You have studied this in all
The
these
grain,
things.
the grain
Yes.
which lies on the same axis, linear axis.
Yeah, equiaxed means mostly, as you said, it is mostly of spherical shape. The grains of spherical shape. So that equiaxed means around the both sides. Just one part is the mirror image of the other part, isn't it? So equiaxed grain, axis, equiaxed. Both side it is almost mirror image type. If it is not exactly, almost. Okay. So that type of grain, you have already studied this in your material science. So therefore, equiaxed grains are formed. Other types of grains are also there. Okay. Those things, it will not come here since you have already studied. Chill grains are there. Chill grains, just like a needle shape. Needle shape grains are also there. So this is equiaxed grain means, and one more type of grain is there, columnar grain. COLUMNAR, columnar grains. It means that the grains are almost column type, vertical columns type. So this is equiaxed grain means just like it is almost, it is not exactly spherical. It is resembling the spherical shape. That is why it is called as the equiaxed grain. So therefore, here rapid cooling promotes, rapid cooling or chilling of liquid metal promotes the formation of fine equiaxed grain structure. Promotes the formation of fine equiaxed grain structure. Okay, when casting is carried out in, that is cold molds. Mold is very cold, so that is atmospheric temperature. That time what happens? The temperature of the mold is very less. It means that atmospheric temperature, liquid metal temperature is very high, 660 degrees centigrade or 700 degrees centigrade. Since the temperature difference is very high, that is 700 degrees centigrade, and mold is at normal temperature 25 degrees centigrade or 30 degrees centigrade atmospheric temperature. So difference is too much, 700 to 30 degrees centigrade. Difference is 670 degrees centigrade. So therefore, very fast cooling takes place when the temperature difference is more. Due to this fast cooling, it will show the chilling or super cooling or fast cooling, rapid cooling. Then it produces the equiaxed, fine equiaxed. What is the meaning of fine equiaxed? Fine nothing but very small equiaxed grain structure is produced. Okay, instead of fine, if it is here coarse, coarse means bigger. So here it is fine equiaxed grain structures are produced in the solid metal. Okay, when it is possible means when the mold is mold is at room temperature, and liquid metal is poured at certain definitely higher temperature like 700 degrees centigrade or 750 degrees centigrade. So this is about the thermal method. So by controlling the temperature, by monitoring the temperature, the fine equiacid grain can be produced. If what happens if the other way, if the temperature cooling rate is slow, that also you should ask. If the temperature or the cooling rate is slow, it means that the pouring temperature, liquid metal temperature is 700 degrees centigrade and mold is maintained at 400 degrees centigrade. For example, mold is sometimes we preheat the mold. Mold is going to be preheated. So why means if you want the coarse structure, coarse means bigger grains. If you want the bigger grains, then the cooling has to be taken place very slowly. For that purpose, what we do, we preheat the mold cavity or mold box, so that what happens, cooling is controlled. Slowly it is taking place. Because of that, bigger grains we will get. Like that, this method is called as the thermal method. Okay. Next method of controlling or to have the finer grains or coarser grain, it is depending upon the chemical combination. What is that chemical combination? You can see here. The next one is chemical method. Chemical methods involve addition of some elements called grain refiners. Some chemicals we are going to add into the liquid metal. What those elements, what chemical agents we are adding into the liquid metal. So those materials or those chemical agents will promote formation of more nuclei in the liquid metal, and more nuclei are formed. So therefore, fine grains you will get. Fine grains nothing but very small grains. So those small grains you will get. So therefore, that is called as chemical method. What is that chemical method? What chemical we are adding means, you can see here, aluminium titanium carbide, AlTiC. AlTiC means this is titanium carbide, Al. One alloy we will take, that alloy which is composed of aluminium and titanium carbide, which is in the solid form. Okay, this is in the solid powder form. And or aluminium titanium boride, TIB, TIC or TIB. This powder we are going to take, either this powder or this powder we are going to take, and then we are going to add into the liquid metal during pouring. So before pouring or during pouring, that time what happens, it will initiate. This is, since it is in the solid shape or solid form, and we are adding this solid into the liquid metal, then what happens, this forms the nuclei. More nuclei are going to form. Then fine grains, very very fine grain, smaller grains you will get. So if you don't want smaller grain, then you need not have to add anything. Slowly you just cool it in the liquid metal, you will get you cool the liquid metal slowly, so that you will get the bigger grains. So therefore, in order to have the fine grains, we have to add either aluminium titanium carbide or titanium boride alloy powder, fine powder in nano powder. That nano size powder to be added into the liquid metal before pouring. So then we will get the required grain structure. This is about the chemical method. I hope these two methods you have understood. If not, you can ask me anytime. Then is mechanical method. One more method is mechanical method. We can have the fine grain structure by using this method also, mechanical method. What is that mechanical method? Mechanical refining method involves stirring and or agitation, stirring of the liquid metal. Okay. By stirring of the liquid metal also, we will get the fine grain structure. What is the meaning of stirring? Already I had explained in the previous class what is the stirring mechanism. So using this diagram I had explained. There is a liquid metal and there is a stirrer here. This stirrer is connected to electric motor, so that this rotates. There is a fan type of arrangement, at the bottom of the liquid metal here you can see. So that when this rotates, this is called as stirring mechanism. Okay, so here you can see mechanical refining method involves stirring, or it is also called as agitation, mechanical agitation or mechanical vibration of the melt nothing but liquid metal during solidification by using ultrasonic or electromagnetic mechanical stirring methods. See here. So how this can be carried out, stirring action or agitation can be carried out means, so during solidification, so we can use this ultrasonic or electromagnetic and mechanical stirring methods. This is mechanical stirring, just now it is shown. This method is called as mechanical stirring method. So other than that, there are two more methods mentioned: electromagnetic method and ultrasonic method. These ultrasonic and electromagnetic methods, they induces vibration. What is the meaning of ultrasonic? Ultrasonic means it is nothing but vibration. Okay, a vibration beyond the audible range of sound. So that range is called as, that noise is called as ultrasonic sound. So using that ultrasound or electromagnetic system, we are going to create a small agitation. So because of that, the minute particles are going to deposit on the solid surfaces. Therefore, fine grains are going to be produced. Normally, this is very expensive and very difficult to produce, the casting. Which one? Mechanical method. It is expensive and not that much easy. So therefore, normally what we do to get the fine grain structure, we follow the chemical method by adding these things or by thermal method. So by thermal method and chemical method, it is the most commonly used methods of producing fine grains structure in the aluminium metal. Okay, mechanical method, it is very rare because it is very difficult. Okay, so this is about the how to obtain the fine grain structure or how to control the parameters, grain refinement. Any doubt in this question you can ask now, sorry, in this topic.
No, sir, no doubt.
What about others?
No, sir.
ಯಾರಪ್ಪ ಇಬ್ರು ಲಾಬಿಯಲ್ಲಿದ್ದಾರೆ? ಪುನೀತ್ ಕುಮಾರ್ ಎಸ್, ಕೆಜಿ ಸತೀಶ್. What is happening in KG Satish? Network problem?
Yes, sir. Network problem, sir.
ಎಷ್ಟೊತ್ತಾಯ್ತಪ್ಪ ಕ್ಲಾಸಿಂದ ಹೊರಗಡೆ ಹೋಗಿ?
Sir, on 5 minutes ಆಗಿತ್ತು sir.
Okay. So now we are just now I explained that you were there during explanation of this thermal method or chemical method.
Yes, sir.
Okay. So this is actually the last topic of this chapter, pouring temperature. What are the factors which are controlling the grain size and which are controlling the properties of the materials? It is one more important factor is pouring temperature. At what temperature of the liquid metal it should be made to, or it should be allowed it to flow into liquid, mold cavity. So that is the required thing. See here, for example, aluminium melting temperature is how much? Melting temperature of aluminium is 660 degrees centigrade. 660 degrees centigrade. Melting temperature and freezing temperature, both are same. Both are same or different? Can anybody tell me what is freezing temperature? What is melting temperature? Please unmute and and tell me now
Sir,
what is.
in freezing in freezing temperature, the solid material, the liquid material will transform into solid material.
Yeah.
In melting temperature, the liquid material will be transformed into solid material. That's the difference, sir.
No, ಎರಡು ಸೇಮ್ ಹೇಳಿದ್ಯಲ್ಲಪ್ಪ. Both you said same. Just it should have told opposite. ಒಂದ್ಸರಿ ಹೇಳು. Once again you tell me.
Sir, melting temperature means the transformation of solid material to liquid material.
Exactly, correct. Then
freezing temperature is nothing but opposite of solidification, sir. I mean, that is melting temperature.
yes, what happens? Melting temperature nothing but conversion or transformation of solid into liquid. At what temperature the solid material transforms into liquid state, that is called as melting. Okay, melting temperature. It is 660 degrees centigrade for aluminium. Transformation of solid aluminium into liquid aluminium takes place at 660 degrees centigrade. Okay. Then in the reverse direction, if you come, there is liquid metal or liquid aluminium. At what temperature the liquid aluminium freezes into solid, that is freezing temperature, transformed into solid aluminium. So at what temperature it happens? Anybody? At what temperature freezing takes place? Quick.
0 degrees.
Huh? Yes. At what temperature the freezing of aluminium takes place?
Less than 660 degrees Celsius.
It is at 660 degrees centigrade?
Less than 660 degrees Celsius, sir.
Less than 660 degrees centigrade. Why it is less than 660 degrees centigrade?
Because the aluminium melts at 660 degrees Celsius, sir. So less than means it gets solidifies.
Okay, very good. But Harsha, you have studied the material science already. You have also studied the heating curves and cooling curves for pure metal. Pure metal. Alloy is different. Pure metal is different. Okay, alloy nothing but mixture of two or more materials. It is going to form alloy. Only single metal, it is called as pure metal. Now, when we talk about the pure aluminium, if you are heating the metal from room temperature, that is at the solid condition, if you want to convert it into liquid condition, then so it melts at 660 degrees centigrade at constant temperature. Okay, at 660 degrees centigrade it melts. So it is at the constant temperature. Then while cooling also, the freezing of metal takes place at 660 degrees centigrade itself. At 660 degrees centigrade itself. While cooling, the 660 degrees centigrade temperature is the barrier below which the metal is solid, above which the metal is liquid. While heating, same thing happens. Below 660 degrees centigrade, it is solid, and above 660 degrees centigrade, it is liquid. So freezing temperature and melting temperature for pure metal, it is same. It is, I'm telling you repeatedly, for pure metal. Okay, pure aluminium, pure iron, pure copper, whichever may be the pure. So then pure metal, it is same. It is melting temperature and freezing temperature. We call it as freezing temperature while cooling, and we call it as melting temperature while heating. Okay, you must have studied about the cooling curves. See this curve. Can you see this curve? You are seeing this curve? You are able to see? Matadrappa.
Yes, sir. Yes, sir.
Okay. See, this cooling curve, if you look at it, this is for pure metal. This is for pure metal. See now, where I am kept the cursor, it is the liquid temperature. It is more around 700 degrees centigrade. Assume that at what temperature we are pouring the liquid metal? At 700 degrees centigrade or 750 degrees centigrade at this point. Then with the lapse of time, over a period of time, it loses the heat, but still liquid only. It is losing the heat continuously. This graph is plotted temperature versus time. Temperature versus time. With the lapse of time, so the temperature is dropping down and it reaches 660 degrees centigrade. See here, at this corner, liquid phase, you can see. Liquid phase. It is at this point, it is 100% liquid at 660 degrees centigrade. Understand? Then, see, there is a gap of time or lapse of time. From this point to this point, so much of time is elapsed. See, from here to here. So, temperature is constant, but time is increased. With the lapse of this time, temperature is constant, it is not less. It is not cooled down. Temperature is same. Then at this point of time, see at this point of time, it has converted into solid phase. What is the temperature? It is the same 660 degrees centigrade. Here also 660, here also 660. Then this point is called as freezing point. Okay, at this point, the liquid metal completely freezes into solid. Once all the metal frozen or it has become solid, then you can see the temperature decrease up to room temperature. Understand? This is called as cooling curve. This curve already you have studied in your material science. Also, I had explained in this subject before starting module 3 or at the beginning of the module 3, I had explained this diagram. You cannot say no because I have explained it. You understood this diagram? Say yes or no first.
Yes, sir.
Remaining students, Artha Aitendrappa, this is clear. Is it clear? Then, for example, if you want the heating curve, same curve in the reverse direction, it becomes heating. Only cooling curves are available in the diagram here. These are all cooling curves only. Okay, now you look at this diagram. Now you look at heating diagram. Don't worry about all these lines. I'm going to take this solid, melting and liquid. Only up to this stage I will take. Further it is not required for me. This is for steam formation. This diagram is for steam formation. I don't want the subsequent steps, vaporization and other things I don't want. Now, heating curve, how it will be, the metal heating curve. See, the aluminium or any material, at room temperature, it is here, at room temperature. Then from room temperature, you are going to heat. Then it is going to, temperature is going to increase like this, up to this point. This is the start. At this point, the metal is completely solid. At this point, the metal is completely solid. Okay. Then 100% solid at constant temperature. Once it reaches the saturation temperature of 660 degrees centigrade, then slowly the metals start to transform into liquid metal. So therefore, slowly, gradually, with increase in time, see the time you can see. This is the time. So, and temperature. See now, with even the increasing the temperature, see here there is no increase in temperature. What is happening? Constant temperature is maintained. Here it is 100% solid, but here it is 100% liquid. Okay. So this point is called as melting. See here, melting. So melting takes place at this temperature. So for that matter, melting temperature and freezing temperature both are same. While heating, we call it as melting temperature. While cooling, we call it as freezing temperature. That you should remember. Understand?
Yes, sir. Understood.
Okay. Then what happens to that temperature? This one. While cooling, lapse of time, continuously the heat is lost, but the temperature is maintained constant. How it maintains the constant temperature? Can anybody tell me? While heating also, how the constant temperature will be maintained? When you are supplying the heat continuously to convert a solid into liquid, you are supplying continuously the heat, but temperature there is no increase. What happens? Who will answer? Anybody? Session is open to you, all students, to give the answer. One by one going out. Yes. Anyway. Karthike, ಹೇಳ್ತೀನಪ್ಪ?
Sir.
What happens? Why constant temperature?
Sir, by giving a constant temperature means by heating the any material at constant rate.
No. Then
for example, if we are heating any material at 30 degrees Celsius, we need to maintain the same temperature. So then we can achieve that goal, sir. I mean, we can get constant temperature.
No. We are not trying to achieve anything. I want to melt aluminium, that's all. I want to melt aluminium. We are continuously keep on supplying the heat. Okay. First heat is called a sensible heat from solid within the solid. Then it reaches latent heat. Okay. There are different types of heats you might have studied. Sensible heat, latent heat, superheat. Studied, no? Yes or no?
Yes, sir.
What is latent heat? Sensible heat means it will show indication of increase in temperature. Sensible heat. It senses. So insensible. It senses and the temperature start increasing. Up to what temperature it will increase means up to saturation temperature it will increase. Once it reaches the saturation temperature of a particular metal, then there won't be any increase in temperature, but we keep on supplying the heat. Understand this basic concept, you should understand. Then what happens, since whatever the energy you are supplying, that energy will be utilized for conversion of solid into liquid. Okay, that heat is called as latent heat. It will not show any increase in temperature, but heat is there. That heat is utilized for transformation of solid into liquid. Once all this, that is why you can see the constant temperature. Once all the solid is completely transformed into liquid, then you can see increase in temperature. That is called as superheat temperature. Okay, this you have studied in your first year subject, which is called as elements of mechanical engineering. In the steam formation subject chapter you have studied, and in thermodynamics you have studied. Again in material science you have studied heat, superheat, and then latent heat. All these things are the thermodynamic related subjects, topics you might have studied, and then you might be remembering all those things. You don't forget the basic concepts. However, this is about the pouring temperature. Here in this paragraph, it is mentioned that if the aluminum metal temperature is melting temperature is 660 degrees centigrade, what should be the superheat? What should be the pouring temperature? Pouring temperature should be between 700 to 750 degrees centigrade. Less than this, if 660 degrees centigrade is the melting temperature, if you pour at 660 degrees centigrade, then what happens? Immediately it freezes, because freezing temperature and melting temperature both are same for pure metal. That already I told. So while pouring itself, it freezes. Then it cannot reach all the corners of the mold cavity. Therefore, it has to have sufficient fluidity, liquidity. So that what happens, in order to have that fluid character, it has to superheat. See, this is called as superheat. So the metal has to be superheated between 700 to 750 degrees centigrade. It should not go 800 degrees centigrade, 900 degrees centigrade. Again, that much superheating creates so much of other problems. So therefore, good temperature is between 700 to 750 degrees centigrade. Within that temperature, it has to be poured into the mold cavity. Otherwise, so many problems will arise. Like that, this is about the pouring temperature topic of this chapter. And this already I had explained stir casting in the previous class. With this diagram, I had explained. So once again, I'm not going to explain these things. Already it was covered in the previous topic, previous class. So with this, I have completed module 3. Now we are left with only 2 modules. And I will be giving the assignment after this, after you submit the assignment 3. So then I will give you this assignment. Okay. So before that, you go through everything, so that, and mostly next somewhere next class or after next week, we may have one quiz on this topic. Okay. The second module 3, second topic or second chapter type. So in this topic, we will be having melting of non-ferrous metal or non-ferrous foundry properties in this or on this